Hello viewers, welcome back to this course. So today we will start with the lecture 7. So in the previous lecture we have discussed about the integer representation of a number, and we have also discussed a little bit about the floating point representation of a number. So we will continue with from there. So today we will discuss that how the floating point representation of a number is saved in the computer. So for example, suppose in the last class we have discussed that any floating point number in the decimal form, like in the previous class we have converted this 0.75, so that was equal to 11 in the binary form. So now suppose we have numbers, so that numbers is given to me in the form of binary. So suppose I have a number like 0.011, or maybe I have number 1.101, or maybe I have number 111.1. So this one can be presented with the floating point form. So floating point form is that we can write this number as 0.11 into 2 raised to power, because I have taken the 0 here, so it can be written as -1, or this number I can be written as minus 0.1101 into 2 raised to power plus 1, or I can write this number as a 0.1111 into 2 raised to power plus 3. But in the, because we are writing this number in the form of a binary, so in the binary we know that 2 in the decimal form, that can be written as 10 in the binary form, or maybe 3, if I write 3 here, so that can be written as 11 in the binary form. So we can write this number again in the form of 0.11 into 10. So this 10 is not the 10 in the decimal form, it is the binary representation of number 2. So this can be written as -01, and this number I can write is the minus 0.1101 multiplied by 10 plus 01, and this one is 1111 into 2 raised to power plus, so 2 means 10 raised to power 11. So that is the representation of a floating point in the form of binary. So this one I can written as, so now I can how I can save a floating point number. So first I will convert this one into the binary form, and then, so it is a 8-bit computer. So the first bit is for sign, then the next 4 bit I will take for the mantissa part, and this is for exponential part. So and that is the sign of the exponential. So if in this case the mantissa is this one 0.11, and this is 0.1101, and this is 0.1111. So that is the mantissa, and exponential part is -01 plus 01 plus 11. So that is the exponential part. So now suppose I want to save this number in the 8-bit computer. So 0 is for plus sign and 1 is for negative. So I will put here. So mantissa is the next the 4 bits. So but I need this 1 only. So I will put, in this case I will put just 1 1, and that is 0 0, and the exponential part is negative. So I put and 0 1. So, that gives me the number which we have saved this in the computer. So, the same way I can put the next one is the same way. So, if I have a 8-bit computer 1, so I will put here the negative sign, so 1, and then I will put 1 1 0 1 and then 0, so that is the sign for and 0 1. So, in this way if I work with the 8-bit computer, this number can be saved in the memory. So, the next question is that suppose I go with the same one and I have a 8-bit computer. So, what is the maximum number we can save? So, this one is 5. So, in this case what I will do, that is possible for me if I, so that is the sign, so it does not matter. The next 4 digit I can put 1 1 1 1. So, this one I can put, and in the exponential also I can put the 0, that is a positive, and 1 1. So, this number can be written as 0.1111 into 2 raised to power means 10 plus 1 1. So, that is the number we can save. So, it means that 1 1 is means this number is equivalent to 0.1111 into 2 raised to power 3. Okay. So, this one it means I have taken the 3 digits after the decimal here. So, I can write 111.1. So, that is the number we have in the binary form. So, this number I can convert into the decimal form by converting into the decimal form. So, this number is, so I can convert this number 111.1 to, so this one can be written as 2 raised to power 0 plus 2 raised to power 1 plus 2 raised to power 2 plus 2 raised to power minus 1. So, this can be written as 4 plus 2 plus 1, and this is plus 0.5. So, I can write this as a number 7.5. So, this is the largest number we can save in the 8-bit computer. So, I can say that if I have a 8-bit computer, then this is the number 7.5. I can biggest number I can compute, and the lowest one can be minus 7.5. So, that is the number we can deal with in the floating point for the 8-bit computer. The similar way we can define, maybe these days we have bits computers. So, in the bit computer we have, these are the, so in this case the first is for the sign, next, so these are the 52 bits. So, 52 bits is for Mantis part. And the next, this 11 bit, so that is for the exponential. So, it's 52, 11, 63 and 164. So, this is the way a number can be used in the 64 bits. So, definitely in this case my number, I like in the 8-bit computer I was able to calculate only 7.5, the highest number, but in this case the highest number will go will become very big number, because in this case we have 52 bits in the mantissa and 11 bits in the exponential part. So, this way a binary number, a floating point number can be saved in the computer. So, now, so after doing this one, we will define what about the significant digit. So, significant digit, so in order to find the number of significant digits, we convert the number into floating point representation. So, floating point representation means in this case I am taking the normalized form, or I can normalized form. Then the number of digits appears in the mantissa part. Are called number of significant digits. Okay. So, for example, suppose I have a number like this, I have number 0.00346. So, that is my number in the decimal part, but this number is, because in the normalized form I know that the value of here, so this number can be written as point D1, D2, D3, D4, D5. So, in the normalized form the D1 should be less than 1 by beta 1, where beta is the basis I am taking. So, that base is 10, because we are dealing with the decimal form. So, 1 by 10 is 0.1. So, it can be greater than this one. So, it should be greater than 0.1, less than 1. So, that is the normalized form, but here it is 0. So, what I will do, I will write this number as 0.346, and that will write 10 raised to power minus 2. So, in this case I have taken the two numbers on the left hand side. So, I will divide this one. So, in this case now this is my normalized form in the floating point. So, I can, from here I can write that this number has 3 significant digits, because this is a 1, 2 and 3. So, these are the 3 significant digits we can have. Similarly, suppose I have a number like 0.200346 into 10 raised to power maybe 2. So, that is my number in the form. So, in this case, so this is okay, so that is the normalized form. So, I can say that 4 and so all 8 significant digits. So, that is the so in this form we will carry that this number is having the normalized form, and this has the 8 significant digits. So, this is the about the significant digits. Now, we find out that how the errors occurs in the computer. So, for this one I will find out that there are two type of approximation a number. So, first is called rounding of or rounding a number. A number, because we know that in the computer whenever we are dealing with the fractional part we have to approximate the number. So, in that case how we can approximate a number. So, this is done by the rounding of a number. So, this is how we will do that. So, let I suppose I have a number like D1, D2, Dn, Dn plus 1 up to Ds. So, that is the decimal part, before that it is 0 into 10 raised to power. So, 10 raised to power is my base I am taking 10, and then the suppose I have a here the quotient q, exponential part the q. So, this is the number is given to me, and that number is I have written s, means it has s number of significant digits. So, this is in the normalized form. Now, suppose we want to approximate this number. We want to approximate this number with n digits in n significant digits, n significant digits. So, what I will do in this case? So, what I will do is that now I want to approximate this number with n significant digits. So, how we can approximate? So, this is the two way. So, now I will take, I have to look, because here I want to approximate or truncate this number. So, in this case I have to take care that what is this one. So, I have to take care what is my digit value of the digit at n plus 1 at places. So, this number can be written as, so if this number dn plus 1 is greater than equal to 5 and less than 5. So, what will happen in this case? If this number is greater than equal to 5, then the number at nth digit will be added to 1, and in this case I will have my number dn that will be same as dn. So, that is the called the rounding of a number, or we can call it that number, this number has been rounded off, has been rounded. So, in this case my new number, so suppose my this is my x, the exact number. So, I can say that x star is my new number, and this is written as d1 d2 up to dn into 10 raised to power q. So, this is happening when my dn plus 1 is less than 5, and this will be equal to 0.d1 d2 dn plus 1. So, one value will increased, and this will be equal to this one if dn plus 1 is greater than equal to 5. Okay. So, that is called the rounded off. So, this is the way we can do the rounding of a number. The second one is the chopping of a number. So, in this case we do not care what is the value of dn plus 1. So, suppose we have this number, the same number I have dn plus 1 up to ds. So, s number of significant digits 10 raised to power q. So, in this case I want to chop this number using the only n digits. So, now I do not care about what is the value of dn plus 1. So, in this case I just chop this number, and I will approximate this number by 0.d1 d2 up to dn into 10 raised to power q. So, that is my chopping of number. So, in this case if you see that if my dn plus 1 is less than 5, then the rounding of number and the chopping of number is same. So, that should be taken care. So, from here I can say that if dn plus 1 is less than 5, then rounding of or chopping of a number is same. So, that is we have to take care. So, for example, so I take the example 1. So, suppose I take a number 0.24568 into 10 raised to power 2, okay, and I will rounded this number up to 4 decimal. So, in this case 4 decimal means here I want to round. So, in this case my next digit is greater than 1. So, I can write 2457 10 raised to power 2. So, that is the rounded number in this case. And now suppose I have rounded this number. So, now I want to see the what is the error, because this is my x and this is my x star. So, I want to find the error. So, error means I will want to find what is the difference between x and x star. So, from here I can see that my x is 0.245684 into 10 raised to power 2 minus, so this number is 24570 and 0. So, that number I have taken, so this is the rounded number, and so this number becomes the bigger as compared to the previous number. So, from, and I can see that first 3 digits okay. So, it is 0.000 and this is 684 and it is coming from the 700. So, I can put it negative sign here and then it is 0.16 into 10. So, this is minus 0.0016. So, that is the error we have in this number when we have rounded this number up to 4 decimal. So, this error is introduced there. Next thing we want to discuss the errors due to rounding or chopping of a number. So, how much the errors we can find when we rounded off a number or a chopping of a number. Suppose we have a number, so that is the represented by x, which is rounded to 4 decimal. And let the number comes is x star is equal to 0.4387. So, I want to find what is the value of x. So, my x star is given to me and I have rounded the number x up to the 4 decimal. So, in this case, so here it is 7. So, I can say that x can be 0.43865, it can be 0.43866, like this one, or so in this case I can say that my x is always greater than equal to 0.43865. So, this is a number maximum x can be always greater than this one, because now what is the smallest number? The smallest numbers can be, suppose my x is equal to 0.43875. So, if I have this number, then this becomes the 8. So, I can say that this number can be always less than 0.43875. So, I am not putting equal, because equal sign means if it is 4 here, then this number will be 0.4387. So, that is the lower bound of this number and this is the upper bound of this number. So, from here I can write. Now, what I do is I want to see what is the x minus x star. So, I want to find out the error, that what is, how much is the error between x minus x star. So, I will subtract my x star from each of the number. So, it will be 43865 minus 0.4387. This number is 0.43875 minus 0.4387. 87 means it is 0. So, from here I can say that my x minus x star can be less than equal to, from here, so this is 875 going this one, so 0.00005, and this number can be written as, so this is a not a equal sign, is less than, and this one is 870. So, I can minus 0.00005. So, using this number, So, from here I can write that my x minus x star modulus value can be written now as 0.00005. So, this is the number we can have, and this one I can write as half into 10 raised to power minus 4. So, in this case, because we have rounded the number up to 4 decimal, so this is a 10 raised to power minus 4 is coming and half. So, from here I can say that if I take the absolute value of the rounded error, so this is, I can take that absolute round of error. So, that is the round of error. So, this error is always less than equal to half into 10 raised to power minus 4. So, wherever the digit I am rounding, so this can be written as. So, from here I can say that if I am rounding my number at the nth digit, so this is always less than 0.5 into 10 raised to power minus n. So, this is a we can say that the rounded off error is always less than equal to 0.5 10 raised to power minus n, if we are rounding the number after n digits. So, that is the way we can define. Now, so we can say that what about the error due to chopping of a number? So, in the chopping of a number, what we will get? So, in the chopping of the number, we are not rounding this. So, in this case, my x minus x star will be always less than 10 raised to power minus n, because 0.5 will not come, because we are not increasing the number by one digit. So, in this case, my chopping error will be this one. So, that is the error due to the chopping of a number. So, from here I can say that the rounding of error is always half than the chopping of error. So, that is why we always prefer to calculate the rounding of error, because rounding of error is, from here you can see the rounding of error is half of the chopping error. So, that is always useful to go for the rounding error. So, this is about all about the errors due to the rounding off and the chopping off, and in the next lecture we will discuss further about the errors in the computer. Thanks for watching. Thanks.